Okay. All right. Good afternoon, everyone. I'd like to welcome you to our fourth webinar on MICA approved project presentations. And this particular presentation is going to be by Smarter Alloys, who is going to be doing a presentation on capture and conversion of mining low-grade waste heat. And our presenter today is going to be Michael Kantz from Smarter Alloys. But before we jump into the presentation, I just want to give you an idea that we are going to be doing 16 presentations in total of MICA approved project. This is number 4 presentation, and this session is being recorded and will be made available on our website and also available to anybody who requests it from us. This is yet to show you that there are 16 projects approved for MICA's first round of funding, and the one we're speaking to today is Extract Energy, who is receiving a little over $1 million from the MICA network. Okay, another thing I want to let you know is that we do have our open call for proposals open right now. And if you'd like to get more information about our open call, just use your phone, click on this picture here, and the QR code will give you access to our call for proposal process. But at the same time, feel free to contact us via our website, and that information that will be provided to you later on. All right, so now it gives me great pleasure and really honored to have Michael here with us today. Michael, you and Ibrahim are doing amazing work with low-grade heat capture, and looking forward to hearing all about it. So please go ahead.
Thank you, Charles. Let me just share appropriate screen. Can you see my presentation, Charles?
Yeah, go ahead, please. Thank you.
Good. All right. So we know that 2/3 of all energy is lost to waste heat globally. 2/3, that's a huge amount. Even if you've heard this number 1,000 times, like me, hearing it again should really make you think about the situation and ask, do we have a waste heat problem? I'm Michael Kuntz. I'm VP Operations here with Extract Energy, which is a subsidiary of Smarter Alloys. Waste heat is a product of all industrial processes, but it's not all created the same. Within waste heat, we have heat that's above 230 degrees Celsius. This temperatures, this waste heat can be easily recycled or recovered. But 2/3 of our waste heat is below 230 degrees Celsius, which is considered low-grade waste heat because it's extremely difficult to recover efficiently, especially for a vast amount of low-grade waste heat that's below 150 degrees Celsius, where it becomes extremely expensive and difficult to put this waste heat to work. So, ladies and gentlemen, I suggest that we do not have a waste heat problem. We have a low-grade waste heat problem. And this issue is especially relevant to mining, where we estimate that about 4 to 7% of the world's energy consumption is used in resource extraction and processing, and accounts for as much as 24% of operating costs. And it's also 60% more expensive to use energy in remote areas, which is common to the mining industry. So we know that this is a significant problem, and the sources of waste heat in the mining industry include ventilation exhaust, mine dewatering, power generation on site, the smelting process, electric arc furnace, and slag recovery. So there's a vast amount of waste heat sources that are present in the resource extraction industry. So to tackle this problem, as we race towards net zero, Smarter Alloys has introduced the Extract Energy heat engine, which takes low-grade waste heat from industrial sources and turns into clean, carbon-free, low-cost electricity. Our solution taps into industrial processes that generate waste heat. It provides cooling and generates electrical power that can be fed back to the facility to improve overall operational efficiency. What's unique about our system is that it can operate at waste heat streams down to very low temperatures. For example, with a temperature differential of as low as 25 degrees Celsius, we can operate at down to waste heat streams of only 50 degrees Celsius. So really what's needed here is just a temperature differential of 25 degrees Celsius. And with an environmental or atmospheric temperature sink of 25 degrees Celsius, we can then operate at temperatures down to 50 degrees Celsius of a waste heat stream. We have extremely low levelized cost of electricity. It's estimated at this stage to be at $45 per megawatt hour, which makes it competitive with other clean energy solutions. Furthermore, the system is scalable, and we can scale it from very small size, like 10 kilowatts, up to the megawatt scale with 100 kilowatt modular units that can be assembled in series or in parallel. The Dexterous Energy heat engine, it's a shape memory alloy-based heat engine. You may have heard of shape memory alloys or SMAs before. They're widely used in medical devices, such as in this example for a self-inflating stent, where the unique properties or the shape memory effect of this material is used to open arterial blockages. In this case, the SMA material reacts to temperature changes within the body with a reversible solid-state phase transformation that causes a shape recovery. And the specific strength of this shape change that occurs upon heating is quite enormous. In this video, you can see just 4 very small, less than 1 millimeter wires lifting me off the ground. So there's no hidden wires, there's no illusions, there's no magic happening here, it's just material science. So now imagine the power if we take thousands of these wires, bundle them together and have them work together, absorbing heat from a waste heat stream, and then converting that to electricity for useful work. In the principle of operation, in the example heat engine here, you can see waste heat flows through a core that's filled with a bundle of these SMA wire elements. So these wires then absorb the heat from the water and they convert it to mechanical work, which can in turn be used to drive a generator. In the second half of the cycle, the flow changes to cool water. It reverses this phase change and allows us to relax the material. So really, there's a difference between the heat source and the cool sink in temperature, and that temperature required depends on what we call the hysteresis of the material. And with proper material processing, including our patented technology, we can then minimize this range. Charles, my presentation has frozen here.
Yeah, you're good.
I'm just gonna go back one.
Okay.
And
okay.
Sorry.
Maybe turn off your video for bandwidth if you would like to.
Yeah, I'll give it a try. I think it's back now, so hopefully it'll be good. And,
okay, thank you.
So what makes the Dexterous Energy SMA heat engine special is our Smarter Alloys patented multiple memory material. We have a very unique material process that laser programs each millimeter of our wire to be tuned to the temperature of the water as it cools along this core. This allows us to reduce the required approach temperature into the heat engine for heating, as well as decreases the overall temperature differential between the source and the sink that's required, thereby increasing our conversion efficiency compared to the ideal Carnot cycle. The improved efficiency and lower approach temperatures make the Dexterous Energy heat engine suitable for a wide range of industrial operations that would normally not be economical for waste heat to power applications. For example, a very close competitive technology we consider the organic Rankine cycle. We can operate at lower temperatures than the organic Rankine cycle, which is typically only effective at temperatures above 150 degrees Celsius for efficient operation. Our low capital cost requirements, the fact that our engine is very simplistic in design, has low complexity, as well as reduced operating, MRO, and capital expenditures for installation, mean that our payback period is very short compared to the organic Rankine cycle. So what we see is that Dexterous Energy becomes a far more compelling option for waste heat to power applications at temperatures below 150 degrees Celsius. Really, there's no other commercially viable technology that can operate in industries that demand a competitive internal rate of return for a clean tech investment such as this. So as we roll out this technology, we're looking at 3 main scale horizons. The first one being small scale industrial, that's focusing on really smaller scale heat engines like data centers and remote industrial facilities. But really our primary markets for this technology is in primary power and large industrial operations. For example, remote mining operations, mineral processing, natural gas compressor stations, distillation operations, the oil and gas industry, the Canadian oil sands SAGD operations, combined heat and power operations, and primary power generation. Beyond this, though, we also see a fantastic opportunity in primary power from geothermal or hydrothermal sources. So the low temperature, shallow wells that are used in natural gas resource extraction, it provides a perfect potential heat source in those wells that are about 3,000 meters or shallower, which provide temperatures at around 150 degrees Celsius and can support theoretical power output of about 5 megawatts. So this provides this fantastic stewardship incentive for decommissioned oil and gas wells, of which we see over 1 million that are going to have to be decommissioned in the next few years. Just note that we also are planning pilot projects at a number of different facilities that fit these descriptions over the next year or so. Our commercialization strategy really involves a couple of different stages. Initially, we see just a scaling up of our production operations of our proprietary SMA material in-house. So working with our pilot partners to launch the product, get it into industry. As we grow, though, we see a pivot to providing purchase power agreements, coupled with distribution partnerships for global market penetration. So outsourcing a balance of the plant equipment while we focus on manufacturing the material, our proprietary material. And then finally, we envision licensing and material supply agreements with licensed manufacturers that allows us to integrate this technology directly into industrial equipment that would be the source of the waste heat. So bolting on the heat engine to, for example, combined heat and power operations. We know that low-grade heat is all around us, especially in the mining industry. This presents a fantastic opportunity for savings with extract energy. From a bottom-up approach, we estimate a conservative feasible potential of about 6.5 gigawatts in North America and 10.6 gigawatts in Europe and Asia across hundreds of thousands of industrial sites. Beyond waste heat, the geothermal opportunity is massive, with over 1 million natural gas wells that need to be decommissioned in the coming years. From a top-down analysis, the waste heat technical potential of the total addressable market is about $1.2 trillion for low-grade waste heat to power. But we're more excited about the potential to offset hundreds of gigatons of carbon emissions by improving process efficiency through low-grade waste heat recovery. To date, we've raised millions of dollars in non-dilutive funding for the development, scale-up, and pilot testing of the extract energy system, including from the Ontario Centre of Innovation, Sustainable Development Technology Canada, Breakthrough Energy Solutions Canada, NRC, IRAP, and Mars, in addition to the MICA funding and other funding that we're going to announce in the next few weeks. We were the first prize winner of the USCI Solutions 2030 Target GHG competition out of over 200 international clean tech startups. And we've gone from a benchtop observation of just 10 watts to a 5 kilowatt demonstration unit in 3 short years. This year, we've got a series of field pilot tests planned and in process for performance validation, which is going to enable us to go to market for smaller scale applications while continuing to scale up our modular system to 1 megawatt within the next few years. For example, looking at the pilot operations, we just completed a pilot site evaluation at HCE Energy in Hamilton, Ontario during Q3 and Q4 of this year. This site is a district heating site for Hamilton, Ontario. It also has a combined heat and power unit on site. So we installed our shipping container at this site and had it operational within a few short hours after tapping into their hot water supply. Continuing on with pilot operations, we are happy to announce new funding through MICA, as well as Emissions Reductions Alberta and NGIF. This is going to support our pilot operations, including the scale up of the unit from 10 kilowatts to 100 kilowatts and beyond, and then provide funding for these pilot site trials and resource industries, including mining and mineral processing, oil and gas. So potential sites that we see coming online are in mining operations, smelting and processing, foundry and forge operations, as well as SAGD operations, refining and distillation, and natural gas compressor stations. The objective of the MICA project is to validate the electric energy heat engine for improved efficiency and reduced GHG emissions in mining applications. And it's going to allow us to also develop a supply chain and distribution partnerships and capacity for scaling the solution. The milestones within our project include scaling up the pilot system. It's going to happen over the course of the next few quarters, which is going to happen alongside of pilot site identification and preparation. And then again, performing the field trials at a pilot site or multiple pilot sites to validate the technology. Currently, we've got a wide range of partners that we're either involved in with funding, providing leadership and guidance and networking opportunities, or providing either confirmed pilot sites or potential pilot sites that we're currently evaluating. And you can see there's a wide range of different sites that we are and partners that we're looking at and partnering with right now. So a quick background about our company. We are, the parent company is Smarter Alloys. This is the technology development holding company. So within Smarter Alloys, we've got a number of different subsidiaries that are basically aligned with each vertical that we operate in. We do have commercialized technology based on our patented material processing technology in the medical device space, which includes Smart Arch and Paradigm, which are really dentistry focused materials, dentistry focused devices and products. We're also active in the automotive and aerospace interior industries through Asonic, which is an actuation division of Smarter Alloys, as well as contract design and manufacturing, which is our SMA lab vertical. But our largest subsidiary by far is Extract Energy, and this is the clean tech vertical that has been formed to commercialize our smarter materials, multiple memory material technology within the clean tech industry. So we've got a very well-established leadership team that has a significant amount of experience in commercializing these innovations, again, and taking our technology from idea to invoice in the medical and automotive fields. So we're very excited about, again, the progress we're being made in Extract and the potential opportunities. So with that, I'm happy to take any questions about the project or the technology.
Awesome. Thank you so much, Michael. Michael, if you just go back one slide, please. Just go back one slide. Yeah, exactly. There you go. Maybe leave this one up here just so people can better see who is who at Extract Energy Smarter Alloys for contacting you and stuff like that. But look, thank you for the presentation. Look, low grade heat, right? 2/3 of the heat is lost. That's amazing. That's actually crazy to even think about it. My first question for you is there like an upper limit of the technology, and is there like a lower limit? I mean, for example, can somebody buy one that they can use at the house? Is it a size that's that small? And also from an industrial application, I know you can kind of put them in parallel, but is there an upper limit as to what this technology can do?
So great question, Charles. On the lower limit, we are limited by economies of scale with respect to the equipment. And so we haven't yet been able to design a heat engine that would be economical for residential operation. First of all, there's usually not a continuous supply of waste heat in residential operations that would give us continuous operation. And the balance of plant equipment would just be too expensive for such a small scale operation. On the other hand, on the upper limits, really it really becomes down to the amount of waste heat that's available and our ability to control the flow of the water, the wastewater, or the waste heat stream, whatever that the media is, through the heat engine. But we are looking at megawatts of capacity to meet the needs of the different industries that we're servicing, including, for example, a SAGD operation where there's hundreds of and over 100 megawatts of waste heat being generated on site continuously over the course of a full year. From a temperature perspective, our standard material can operate within temperature ranges of 130 degrees Celsius all the way down to 80 degrees Celsius, negative 80 degrees Celsius. And all we really require is a temperature differential between the source of the waste heat as well as a sink that we can dump the heat from the heat engine into. So if, for example, there was a cold sink on site, say the bottom of the lake that's at 2 to 3 degrees Celsius all year long, we could operate with a waste heat stream of as low as 27 to 30 degrees Celsius
Wow.
to generate electricity. Of course,
Wow.
increasing that temperature delta or differential allows us to increase the overall operational efficiency and the power output. But we can operate effectively up to temperatures well above 102 degrees Celsius, and with alloying into additions, create a heat engine that can operate within the full range of low-grade waste heat of up to 230 degrees Celsius.
All right, thank you. Thank you for that answer. All right, I'm going to open up the floor for others to ask questions. So please unmute yourself and ask away. Thank you.
Thanks, Charles. Thanks, Michael. That's a very interesting presentation. I particularly liked the slide that showed your milestones. Great to see the growth and development that you guys are experiencing. My question is around sort of maintenance. What are the requirements for heat engine operation?
Great question. Thank you. So the heat engine does operate at much lower speeds than, say, an organic Rankine cycle, which is a turbine-based technology. So we have far less moving components and far less critical components that require very precise tolerances to operate in. So we're able to operate with far less MRO costs than a competitive technology that has far higher requirements. Basically, we're expecting about $1,000 per year per megawatt, I believe, is the number that we're looking at to basically operate and maintain the heat engine. The required maintenance is just greasing of bearing surfaces, inspection of the unit itself, as well as a general cleaning. But it's very tolerant of say different water quality or different waste heat stream quality, including say debris or acidic or basic solutions. So we're quite able to tolerate scale as well, because the fact that the material that's constantly moving is less likely to have a buildup of scale or other sediments within the device itself.
All right, thank you for that answer, and thanks for the question as well. Yeah, my next question is concerning the whole idea around installation timeframes. And this is a question that we get asked by operators who are looking to adopt a technology, because sometimes, the time to install can be excessive in terms of time frame, especially when operations need to shut things down and get you to come inside and install something. So could you just comment on the time to install, and maybe even comment on how scale affects timeline to install, and also maybe mention around the areas of availability of the of your hardware to install? Like, can you do like 10 installations a year? Maybe comment on that piece, please.
Yeah, again, very good question, Charles. So far, our experience with installation time has been very fast. The limited number of pilots we've run so far, we've been able to install this on sites within less than a day, which is, of course, a very short time frame, which would really require a very non-obtrusive or non-intrusive presence on the site that we were piloting with. Of course, the actual time to install the system would depend on the site. For example, as we look at pilots sites within the oil sands, it really depends on the distance that we have to run from the existing dry coolers to where the pilot will be, the pilot heat engine will be located, and where we can tap into that waste heat source. But we expect, again, very minimal installation time and installation costs. And it really does depend on the site and what existing infrastructure is already there. For example, if there is already a dry cooler or a cooling tower that's been built to deal with the existing waste heat, we can basically insert ourselves between the operation and that dry cooler to reduce reduce the load on the dry cooler, which can then be used as our cool temperature sink for dumping the leftover energy from the heat engine. But we do expect very small capital expenditures relative to other competing technologies in the waste heat to power space, as well as very short installation times. Our capacity, really, we're still ramping that up, and still at the pilot stage, so it really depends on the growth of the company, and as we launch, we expect to be able to support a wide range of different installations.
Awesome. Thank you for that answer, Michael. Really appreciate that. All right.
One
Again,
thing I just want to add on that, Charles,
Yeah,
is
please go ahead.
also the fact that, because it is easy to install and very light footprint, it is also very easy to move to different locations. So as the needs of the site change, it's possible to package it up, move it on the skid to another location, and again have it operational very quickly.
Gotcha. Thank you. Thank you for that. All right. Again, I'm going to open up the floor to one more questions. Please unmute yourself and ask your question. Thank you. All right. I do have a follow-up question from a question that was asked previously about maintenance. Maybe just mention, what are the moving parts? Is there a moving part that needs to be changed regularly in your system? Maybe you can comment on that just so people can get an idea on what to expect when they have one installed and running it long term.
Yes. So there is mechanical components that move. The material itself is mechanical, so it does move and expand and contract. And then that's coupled to a conversion mechanism, which takes that mechanical motion, converts it to electricity. And in some cases, we're using a crank slider that's coupled with a gearbox and a generator. So those components have been sized and designed. I've earned about a 10-year lifespan. The material itself is subject to fatigue. So we are currently evaluating that material and expect it to last between 5 to 10 years, depending on the frequency of operation and how much we're actually driving the material. The way to improve the life cycle of the material is to design it with strain in mind, so limit the amount of strain we put in the material. And also through our patented technology, we have the ability to improve the overall fatigue performance through the multiple memory material processing technology. So it's a bit of a proprietary secret that allows us to expand the lifespan of the material to get to that 5 to 10 year cycle life.
Gotcha. Yeah, maybe another question I have for you is, so if you were to, go to a mining company, is there any position title in the mining company? Who is it that you'd want to speak to at a mining operation? Just based on maybe what the work you've been doing already, is there a position, a title, a department that you want to target at a mining operation?
It really depends. I mean, the organizations we've talked to so far have a really diverse range of people who are interested in this. Of course, anybody that's interested or involved in operations and operation efficiency, or has to deal with waste heat, is someone who would be interested in speaking with us, as well as anybody who's interested in reducing the carbon footprint of mining operations and looking for waste heat to power applications to deal with some of the waste heat. So we've talked to a broad range of people so far, and everyone has a very unique background and position. Gotcha.
Thank you for that. And I do have one more question for you, Michael. And this question is around the idea that this industry that we work in is a show me industry, right? So if somebody wants to see the technology in operation, is there a test site they can go to look at it and actually see one in operation? Maybe just give your thoughts on that.
Yep. So we are very interested in demonstrating the technology through pilot sites. We do have a couple that are being lined up for early 2023, and we're happy to provide that information. If you were to contact us and get in touch, we'd be able to basically provide the information of when that pilot will be happening, as well as provide access to that pilot when available. And if you're interested in running a pilot at your site, feel free to reach out, and we're happy to provide more information about the current status and our expectations and schedules for the next year.
All right. Thank you very much, Michael, for the answers. Folks, there you have it. I guess it's waste low-grade heat no more, because Extract Energy is here to turn that waste low-grade heat into electricity, into energy that can be utilized again. Contact details for Extract Energy are available. Just maybe play back the presentation and you can get some of the contact details there. But Michael, I want to thank you for taking the time to do this presentation, and looking forward to all the great things that Extract Energy is going to be doing over the next couple of years. So thank you for your time.
Thanks, Charles. Thanks very much.
Awesome.
Thank you.